So I thought I would begin. We'll need it later. I want to deal with a special case of this particular fact. Recall that last time we showed that if we had a chord of a circle, that there were two angles, the angle subtended by the chord at the center and the angle subtended by the chord at any point on the circumference, on the same side of the chord as the center. And we said that, and we actually showed that under those circumstances, the angle at the center, subtended at the center, was twice the angle subtended at the circumference, no matter where that point was for the smaller angle. Now, there's a special case of this that I want to draw to your attention. I mean, it's the case that will be familiar, I think. The case that this particular chord, that the chord is actually a diameter. So that the case that we move this chord up until it passes through the center. When that happens, this angle phi clearly becomes a sum of two right angles, because these two lines then simply become identified with the diameter. They spread right out, and that means that the angle here becomes an angle like that, which is 180 degrees, or 2 pi. So 1/2 of it is pi, and that means that that angle up there is a right angle. So if we draw a diameter of a circle, and then we put in 1/2 the circle an angle in this way, it will necessarily be a right angle. So let's remember that. Good. Now, that was just to profit in a particular case of what we did last time. See if I can. Oh yes, now I'm almost back where I left off last time. We were in the process, we had just begun to discuss regular hexagon, and we wanted to construct it. And what we persuaded ourselves of, I hope, was that to construct a regular hexagon, we would have to construct a triangle, an isosceles triangle, which was such that these two angles here at the base, the two equal angles, were equal to twice the remaining angle. So we persuaded ourselves that it was enough to do that, and our purpose today is to construct this triangle, and that will take up the whole hour and perhaps even a little more. And I think there's something to be said. Just let me get started here. So what I said was, so don't forget this, and don't forget the other theorem, that to construct that particular isosceles triangle, we would have to do two things that have to be explained. So this was proposition 4.10, and that's our purpose today, to prove that proposition, which is to construct that triangle, and it will be a consequence of three other propositions. Now, let me just say something. There's some picking up. It's a little hard to sort out these. Let me remind you in general of what we're doing, just so we recall. So our ultimate purpose over the course of the whole year is to acquire a feeling for modern number theory, especially for a few of the many conjectural links between algebraic irrationalities on the one hand, and on the other, the Riemann zeta function, and implicitly various similar functions. So the rogue's yarn that will run through much of the material is the algebraic symmetry to which the name of Galois is attached, and of which we spoke before, and which I want to introduce in as concrete and as appealing a way as possible, and in a way that linked it in a manner that is certainly anachronous, but not entirely factitious, with classical mathematics. So apart from its intrinsic appeal, this was the reason for treating the construction of the pentagon. And our task today will be to acquire some feel for this construction. It won't be easy. We have to spend an hour on what I think is genuinely difficult mathematics, and I don't think we should be discouraged, or you should be discouraged if you don't understand everything. What will follow is, in fact, easier. What will follow will be the basic notions of analytic or Cartesian geometry. It will be a little duller, but it'll certainly be easier. Let me anticipate slightly Cartesian geometry, just to make one or two very general remarks before we begin the hard work of today. It is generally accepted that the subject of modern algebra was born during the Renaissance, and that analytic geometry, at least in Descartes' treatment of it, would have been unthinkable without these new algebraic methods. And among other things, it was understood during this period how to solve cubic equations and how to solve quartic equations. I'll come back to them very briefly. Now, we could have used them as an introduction to the algebraic symmetry, but we didn't. I thought that a geometric introduction would be more appealing. But don't forget that there is this other possibility that will be neglected here. Now, let's just, since we're going to say goodbye to Euclid today, let's try to see what parts of Euclid we've actually covered or at least touched upon. You'll recall that there are 13 books in Euclid, and where we are here is at proposition 4.10. So we've got into the fourth book, and we're going to use, in the course of the proof, material from the second book, so proposition 211, and material from the third book, proposition 337 and proposition 332. And we'll see that the key to proposition 211 is the Pythagorean theorem, which I recall was from book 1, book 141. So that means we are covering material from the first 4 books. And I just thought it wouldn't hurt if I just recalled for you what was in the 13 books, just so that you know we're leaving out a lot, just to take a couple of minutes just to recall. So the book 1 contains, as we have seen, contains the most familiar material. It ends basically with the Pythagorean theorem. And book 2, to which we have to return for this proposition 211, deals with what is sometimes called geometrical algebra. That's with material that is somewhat perplexing to a modern reader, as familiar algebraic operations are clothed in very unfamiliar geometric garb, as we'll see today. Book 3 deals by and large with properties of circles that have, even for us, an appealing geometric meaning. And many of them are familiar, I think, from high school. So that we'll need some of them, as I've indicated. Proposition 337 and proposition 332 are quite appealing properties of circles. And then in book 4 basically deals with the inscription of polygons in a circle. So first of all, a triangle in a circle, then a square in a circle, and we saw earlier how that was to be done. A regular hexagon, and I just remind you what a regular hexagon. You will remember, I'm sure, inscribing regular hexagons in the circle. It's easy and fun because the point is, as you'll recall, that the length, each side of the regular hexagon has a length equal to the radius of the circle. So all you do is you arrange it so that your compass has one point here and the other point here, and then you start to mark out those 6 lengths, and you come back where you started. And that's very easy. And that's part of book 4. Otherwise, in book 4, what is constructed, apart from the triangle and the square, is what is inscribed in the circle is the regular pentagon, regular hexagon, which, as I say, is easy, and a regular pentadecagon with 15 sides. And once you have the regular pentagon inscribed in a circle, and once you have a triangle inscribed in a circle, well, 15 is 3 times 5. It's relatively easy to inscribe a regular 15-sided polygon in a circle. So what we are doing then, what we will have done in some sense, very briefly, but is in these 3 lectures is to reach the end of book 4, more or less. We're leaving out a lot of material. Then I just tell you, just so that in case you want to go and look at it yourself. So the 5th book has quite a different character. It treats Eudoxus' theory of proportions. And then the 6th book, which we didn't get, treats on the basis of book 5, largely of similar figures, especially of similar triangles, so that it covers a lot of material with which you're familiar from, or may very well be familiar from high school. So presumably it wasn't treated in high school with the help of the theory of proportions, or the theory of proportions was taken for granted. Now, books 7, 8, and 9 treat of numbers and number theory. So we may come back to them only briefly. Now, actually, in some sense, from the point of view of our later algebraic analysis of Euclidean constructions, book 10 is the most interesting. We shall show that Euclidean constructions amount, in algebraic terms, to repeatedly adding, subtracting, multiplying, and dividing numbers, and repeatedly forming their square roots. This is the point made by Descartes in the beginning of his introduction of analytic geometry. Now, this book, book 10, studies in geometric terms a number so obtained. And what Heath has done, fortunately for us, just to give you an idea of what kind of numbers are studied, Heath has gone, in his comments, has simply taken all these numbers and written them down in modern terms. So you can see the various special kinds of numbers that Euclid studies in his in book 10, and they're all numbers that can be obtained by repeatedly extracting square roots. So we have one square root here, square root of 1 plus k squared. We add k to it, and then we take another square root, and we add to that something quite similar. Or here we have a square root here. We've divided it into something else. We subtracted it from 1, and then we've taken a square root, and then we multiplied by a 4th root, which is, of course, as is indicated up here, just a square root taken twice. So now we don't want to, we want an abstract analysis of these geometric constructions. We want to understand why only square roots come up, and this will be the purpose of, this is the purpose of introducing the analytic geometry. So just to end up, there's books 11, 12, and 13. Book 11 is actually, if you're familiar with linear algebra, it's linear algebra. So treats lines and planes in 3 space. Book 12 is basically a method of exhaustion, so it's simple calculus, if you like. Treats simple plane figures and solid volumes, particular disks or the interior of circles. And then book 13 goes back to and treats the 5 regular solids whose colored pictures we displayed here at one point. Now, what you saw was that the 3 of these solids had sides which were equilateral triangles. One had a side which was a square, and one had a side which was had sides which were regular pentagons. And what we indicated that those 3 figures were intimately related to the numbers square root of 2, square root of 3, and square root of 5. And basically the 13th book goes into a great deal of detail about the relation between algebraic irrationalities of this kind and the 3 regular solids. So it's very hard, very hard book, I suppose. All right, so now we have to go to work. We have nothing, from now to the end of the hour, we have nothing but work ahead of us. Now, we're going to proceed, but I'll first of all try to explain what these 3 supplementary propositions are. 2.11 is for us the key one because it's the one that makes the link with the square root of 5 and therefore with the Pythagorean theorem. So it says to cut a given line so that the rectangle contained by the whole and one of the segments. So think of this as being the given line, goes from here to here. I've just arranged so that the length was 1, thinking in terms of length. But so that the rectangle contained by the whole and one of the segments. So that means the rectangle, one of whose sides is 1, and in whose this picture, one of whose sides is 1 minus x. So its area is, in our terms, 1 times 1 minus x. But remember, in case we forget, just it's worthwhile, I think, to point out once again to remember that this is an anachronism, that for Euclid, an area was not a product of two lengths, but something with its own independent existence. So all that here, just because it's easier for us, I'll represent areas by products, but they're not really products for Euclid. They're areas. Just something God-given. And then is equal to the square on the remaining segment. This is the remaining segment. Its length is x, and its square is x squared. So this is the algebraic relation. And I've put it down there just so we could very quickly make the calculation, namely this relation is equivalent to x squared plus x minus 1 equals 0. And I've anticipated what we're going to do in a little bit, namely I've written down the formula, the usual formula for solving a quadratic equation. So minus b plus or minus the square root of b squared minus 4ac. So b is here is 1. Minus 4ac is minus 4 times 1 times minus 1, which is 5, all divided by 2a, and a is 1. So that's just to stress that the square root of 5, really, we can test easily, has to come out of this. That's x. It has to be positive, so we can't take two minus signs. We have to take square root of 5 minus 1 over 2. And if I'm not mistaken, I'm sure what the golden section is, but I think it's the ratio of these two lengths, which would be, if you make the calculation, it's an interesting algebraic exercise, square root of 5 plus 1 over 2. But the whole purpose of this is just to emphasize that indeed this proposition 2.11 we can test from, with our contemporary understanding, if you like, that we're looking for the square root of 5. And after Euclid has treated the theory of proportions in Book 5, he redoes this proposition as 630, and it's called to cut a given line in extreme and mean ratio, which means, I don't know what it means except this, that 1 over x, that the ratio of the whole length to the longer of the two intervals in which it's been cut, x is the same as the ratio of the longer interval x to the smaller interval. So we have to establish this in Euclid's terms. We have to see how we construct it on the basis of the Pythagorean theorem. Now, proposition 3.37 is incomprehensible. When I was young, Gallic mathematicians used to jump down the throat of young people who were much less incomprehensible than that. They still do, I notice. But there are three propositions here, and they are basically the same. And let me tell you what they are. So if a point be taken outside of a circle, well, that's the point, and that's the circle. And if there fall on the circle two straight lines, well, that's the same as in the first proposition. One proposition is the converse of the other. So here's one of the straight lines, this one. It cuts the circle, which means in particular that it meets the circle, and the other touches it. So in modern terminology, it's tangent to the circle, right there. The rectangle contained by the whole of the straight line which cuts the circle. The whole of the straight line which cuts the circle goes from A to D. And the straight line intercepted on it outside between the point and the convex circumference that's this part, will be equal to the square on the tangent. And this means the square on this line from AB. So the rectangle on AC and AD, which I represent as the product AC, AD, although that is not quite, as I said, that's an anachronism, is equal to the square on AB. That's what this proposition says, and that's the one we'll prove, I think. The first is the converse, which says that well, it says, I think it says that if this condition is satisfied, you have to think of where this line might fall down here or something, but if this condition is satisfied, then indeed it's just fallen so that it's tangent to the circle. So if we draw a line from A to some point B on the circle, and if this condition is satisfied, then we've succeeded in drawing a tangent. But we'll prove the second one. If you prove one, you can pretty much prove the other. And so that's that. We now understand, we haven't proved them yet, we now understand what proposition 2.11 says, we understand what proposition 3.37 says, and now let's try to understand what proposition 3, and we'll come back to proving them, but let's try to understand what the last one means. We'll prove it right away. So, if a straight line touches a circle, and here's the straight line touching the circle, and from the point of contact there be drawn across in the circle a straight line cutting the circle, and that's the line BD. So that's an arbitrary line. I hope that looks arbitrary. And the angles which it makes with the tangent will be equal to the angles in the alternate segments of the circle. What this means is the following. No matter, let's look at this triangle. We know, it was the theorem of which I reminded you at the beginning, that provided BD is fixed, no matter where we place C, this angle doesn't change. And not only does this angle not change, no matter where we place C on this side of BD, but it's always equal to the angle EBD. So the angle EBD is equal to the angle BCD. And this is the angle EBD. So D is fixed, and then C is just an arbitrary point on this side, and this angle in this triangle is equal to the angle EBD. And in an exactly similar way, go the other side, the angle BAD, so the angle in the other side, is equal to the angle here on the other side, so the angle DBF. So let's see if we can't prove that. I think it's the easiest of our three propositions. Oh, before I start, I have to remind you of something. A supplement. So I want to prove one more. I can't prove that directly. Let me appeal to this. We have a circle. This says that the opposite angles of quadrilaterals are equal to two right angles. So that this angle is opposite to ABC way up there, and their sum is a right angle. So that's what this proposition says, and the sum is two right angles. I seem to have trouble there. So let's do that. Unfortunately, something has been erased. There are angle signs here that have been covered over. So recall that they're going to use over and over again this fact. It says angle CAB is equal to angle EDC. Where is CAB? CAB is this angle. So it's an angle built on that chord. But as we know and as we saw, all angles built on that chord are the same. And this is the second one, BDC. So that's the second one. And we do the same thing again, angle ACB. Angle ACB is an angle built on this chord. All angles built on the same chord are the same. So this is the second one, angle ADB. So we have that relation. And now we just do a little, and we just think it over. So angle ADC, which is this one, is made up of this angle and this angle, so it's made up. But this one is ACB, just that. And the other one, this angle is equal, by what we just said, to this one, which is BAC. So this angle is actually equal to this plus this. Got that straight? Right. So I wanted to know, the statement of the proposition said that this angle plus this angle was equal to two right angles, but this angle alone is, by what we've just shown, equal to this plus this. We add this, and we get the three interior angles of a triangle, and that's as we indicated before, and as I took for granted, you'd know this two right angles. The sum of the three interior angles of a triangle is two right angles. So that's this one. And once we have that one, then once we know that, it's relatively easy to prove this. Let's do it. All right. So we want to prove that. Now, we can prove it. It's really two statements. It's a statement about this angle being equal to this, and it's enough to prove the one because we just look at one side or the other. So let's prove, for example, that this angle is equal to that angle. So to do that, we move A. We move A over so that we have a right angle, so that the side BA, which we're now forgetting, is perpendicular to the base. And then, as we'll take for granted, that means that, all right, then let's just do that. Then it will mean it's a diameter of the circle. So what are we trying to show? We're trying to show that this angle is equal to that. Now, angle ADB, by the first remark I made, is we have a diameter. We put this triangle ADB inside a semicircle, necessarily a right angle. So there it is. But angle ADB, right angle, it means since the angle ADB plus the sum of the two other angles of the triangle is two right angles, that means the two other triangles, what's left over is one right angle. So BAD, this angle, ABD is this angle, their sum is a right angle. Right? Now, ABF is also a right angle, because that's how we chose AB. It was perpendicular to this tangent, and that means ABF is made up of three angles there, but in particular made up of this one, FBD, this one, and this small one, which is DBA or ABD. So these two are the same. These two are the same, which means these two are the same. BAD and FBD. Now where are we? That's not quite right. We're showing that BAD is equal to FBD, but we wanted to show that EBD, this, forget whether it's supplementary or complementary, this angle was equal to this. So it's a little bit convoluted, this proof. But what do we say? Well, we say that this one, this angle, plus this one is equal to two right angles. So EBD plus FBD is equal to two right angles. So this plus this is equal to two right angles. And this, which is the other one, BCD, which is supposed to be equal to EBD, this one plus BAD is the sum of two right angles, because what we did was I was very careful to begin the hour with the proof that the sum of the two opposite angles in a quadrilateral, and this kite-like figure is a quadrilateral, was two right angles. So this plus this gives two right angles. This plus this gives two right angles. And since these are equal, then we subtract equals from equals and we get that, which is what we're trying to prove. So we have managed to deal with the last and the easiest of the propositions. And that's not too bad. All right. Now let's come to, we still have two propositions to get through. Let's see if we can't make the construction, taking for granted the two harder propositions. So I'm leaving the worst for the last. So here's the construction. We want to construct a triangle which was, and let me go back, and if I can find the picture of the triangle that we wanted to construct. I'll never get to it. I'll just do something similar. That will remind you of the triangle. This was the Pythagorean pentagram, and remember the triangle is this one. I want that vertical. And you can see it looks pretty much like that one, ABD. So that should be the triangle we're trying to construct. So we want to, so let's go about the construction. We're going to get to ABD, and it has to be right. We want it to be such that this angle, BAD, is equal to 1/2 either this angle or this angle. So we start. We start with just any segment AB. And we divide it by C. This was divided in mean and extreme ratio. This was the proposition 2.11 that we haven't proven. So what this means is that the rectangle on AB and CB is equal to the square on AC. So we're assuming we can do that. We have yet to do it. Now let's see if we can make sense of this diagram. AC is equal to BD. That's how we define BD. Namely, we take this line and then we draw a circle through A with radius AB so that it passes through B. And then we use this length from A to C to cut off this length, D. So we just use a compass like that to mark off a circle of this radius, and that would give us D. So that's the construction. Once we have D, we have the triangle ABD. We just have to show that is the correct triangle. Well, let's try it. AC is equal to BD. That was the construction. And also, the construction was such that A times BC was equal to AC squared. That's how we put C in here, using the one lemma that's not yet to be proven. And that means that AB times BC is equal to BD squared, because we constructed BD to be the BD squared. Now, this is the proposition about circles that we haven't yet proved. We have a circle, which is this circle. The circle that goes through the points A, C, and D. We haven't constructed it, but it can be constructed. So we take the circle going through the points A, C, and D, and we take a point outside it, B. And then from that point B, we have two lines, one of which falls on the circle, as in our proposition, and another one of which cuts it, and cuts it in two places, and another one which cuts it here at D. And what we claim is that this line touches the circle. I don't know. Yes, that's right. This line touches the circle. Why? It's this relationship. Remember, the proposition that we have yet to prove about circles says that if we have one line, and the product, if you like, of these two distances, or the appropriate rectangle, has an area equal to the square on this length, then necessarily this line touches the circle. So it touches the circle, and that means we're back. You see, it goes very complicated. That means we're back in the situation of our previous lemma. We had a line and a circle and a line that touches it. Here we have this circle, this broken circle, and the line BD that touch it. And what we have, what's for us is an arbitrary line, BD, drawn across from this point of tangency to an arbitrary, basically arbitrary point D. Well, this is the point of tangency now called D, and C is an arbitrary point. Now, what does that mean? I don't know if you can see that diagram in this diagram. The labels are unfortunately different. We have this angle, angle BDC, and this angle, the angle DAC. And what our previous statement assures us is that those two angles are equal. So just this and this. Why? Because the first corresponds to this. So if this was the line of tangency, this was the arbitrary line drawn across, the angle between them. Line of tangency, the arbitrary line drawn across, the angle between them. What's it equal to? We take with that chord any point A out here. So we took any point A out here, and what we showed was that this angle, height, was equal to that angle. And that's what we're using. Now, I have trouble, I confess, every time I look at this, I just have trouble passing from that to that, but indeed, it is the same picture, and it allows us to conclude what? It concludes that BDC is equal to angle DAC, so that this is equal to that. So it's an important piece of the proof. Now we should just be able to play with things. To go from there to reach what point? Well, less than anticipate, we want to go to the end. We have angle BCD is equal to twice angle CAD. Remember, I claimed that this was the triangle we were looking for. We have one angle CAD, which is the smaller, and we want to show that these two are equal to are double this. Let's see if we can do it. We just have to play around now with triangles. So let's just go back and see how it works. So angle BCD is equal to angle DAC. Angle CBD, it's hard to keep these things straight. CBD is that. BDA, well, they're equal. This one and this one are equal because this is a triangle lying inside a circle. This side is a radius of the circle. This is another radius. So the two sides are equal, and therefore the opposite angles are equal. So that's this. Angle CBD is equal to angle BDA. But angle BDA is made up of two smaller angles, BDC and CDA. That's clear. Now where can we go from there? Angle BDC is equal to angle DAC. That's what we had from here. So we just put DAC in there. And angle DAC plus CDA. Now we have to think a little bit. So there's a little bit of just playing with the angles, and we have this, the sum of this and this. But once again, we use this basic fact. I begin to think we should have proven it from the very beginning, namely that the sum of the three angles in a triangle is 180 degrees, or two right angles, and that means that DAC, which is fortunately this one, and CDA is fortunately this one, when added together and added to that one, give us two right angles. But the thing is that BCD is just this other piece here, and BCD added to this also gives us two right angles. So this plus this plus this give us two right angles. This plus the same thing give us two right angles. That means that this plus this is equal to that. So that's that part. Now and it goes, let's keep going. We can remember CD is equal. So we have this. Now we want to show that we have two triangles up here that appear to be isosceles. This one and this one. Let's just see if we can be clear to ourselves why. CD is equal to BC, CD is equal to, all right, we have to think about that. Oh, yes. CBD, which is this angle, is equal to BCD, which is this angle. That means that these two angles are equal. Therefore, the corresponding sides are equal. So CD is equal to BD, but BD was so constructed that it was equal to AC. So we have these three all equal. So we have two isosceles triangles. This one, and as we indicated, this one. So that means an angle particular, this isosceles, and this just says that it is isosceles, that these two triangles are equal. But they're equal, and this is this, I mean ADC, CDA, it's the same thing. So this is this, they're equal, their sum is BCD. That means that either one or the other is equal to 1/2 of BCD. So angle BCD is twice CAD or angle DAC. So we're getting there. We have a lot of angles. Angle BCD, just this if we like, or this, is equal to twice this. But I think that's pretty much it. And that's what we're trying to do. We're trying to have angle BCD, which is the same as this, be twice this. So this angle is twice this, and the same as this, so this is also twice that. So that's about as complicated, that's a fairly complicated argument. I suspect that I've lost everyone. I've lost the mathematicians, and I've lost the rest of you. And in fact, I pretty much lost myself. Heath is kind enough, and to say, well, how would anyone arrive at an argument like that? Which is a question one should ask, to run the construction backwards, so to speak. And this is a question that we should ask ourselves, but since he's asked it and answered it, we'll just use. So you have to imagine yourself sitting there idly, with slaves presumably performing all the disagreeable tasks, and just contemplating a pentagon, or just contemplating the triangle you want to construct, which is this one. And just reflecting on its properties, maybe not even wanting to construct it, maybe you simply want to reflect on it and brood idly on its properties. So now, as I said, we did convince ourselves that this triangle sitting in the pentagon had the property that these two angles were twice this. And so we could just say, suppose we have such a triangle? Well, what do? We have nothing better to do, or we've tried all sorts of things. We bisect BDA, because if we bisect BDA, that means this angle, this one or this whole one, was twice this. If we bisect it, we're going to have two angles, same as that. So if we bisect it, we have this angle, same as this angle, same as this angle. Now, that certainly means that DC, we have this angle the same as that. That will mean, easy about isosceles triangles, that this side will be the same as this side. So DC is equal to CA. And then we have to basically recall, and we had this argument before, that this plus this is 180, and this plus this is 180. These two are equal, so this is twice either this or this. That means it's equal to that. So these are equal, means these two sides are equal. So BD is not only equal to, so BC is not only equal to CA, it's also equal to BD. So that, as a consequence, is an indication that I lost track of the logic. It shouldn't be there. Why must BD touch the circle? Well, we don't have any reason. What reason do we have to think that BD must touch the circle? Because we're in that situation, so to speak, backwards. When we had BD touching the circle, then we knew that this angle was equal to this angle. And we can imagine, and it is possible to convince oneself, that there's a converse theorem, namely, when this angle is equal to this angle, then BD touches the circle. So BD touches the circle, and if BD touches the circle, then by that other proposition, the square on BD is equal to the rectangle on BC and AC, because that's the same. We have this line cuts the circle, second line through B that's tangent to the circle, and we have the proposition which says that this square on this side is equal to the rectangle on this and that together. So, but that means, once again, so that BD squared is BC times BA, if you like, in this language. And there we are, but BD squared is AC squared. So what that means is that indeed This particular interval is cut by C, the point where this line that bisects the angle meets the small circle, into extreme and mean ratio. So you have to be familiar with the lot in order to put that together, but you can imagine someone who was young enough and who was mentally alert enough and had time enough would put all those things together, and then he could go backwards to say that indeed he could construct complete the construction that we just went through. And that I seem to have. Oh, just the construction was the same thing. All right. So that leaves us. So, but somehow, I think we haven't seen what we wanted to see from the construction. Namely, we haven't seen how to divide a line in extreme and mean ratio. And that's, so we haven't seen how to use the Pythagorean theorem. And that is, to some extent, the whole point of it, the whole point of the whole discussion, to see how the Pythagorean theorem is used to prove this proposition 2.11. And here's proposition 2.11, I remind you. So to cut a given line so that the rectangle contained by the whole in one of the segments is equal to the square in the remaining segment. That's this first step, AB, BC, B equals AC squared. So we're now constructing this line, which was the initial step of the construction. And here is AB, and the point which is over there, C, becomes H. Now, it's clear what to do. It's a little bit hard in Euclid's terms to verify that that's indeed what has been done, but let's see what to do. So AB is the given line. Then we construct a square on AB, which is easy enough to do, and we bisect this side to give ourselves E. And we join E to B. Now, let's just recall the Pythagorean theorem. So let's just think, in order to have something fixed, that this length is 1. So the remarks in parentheses are, so to speak, modern remarks. So if AB is equal to 1, what's the length of EB? It's the square root of the sum of the squares on the other two sides. The square on this side is 1. The square on this side is 1/2 squared on 1/4. So we get the square root of 5/4, which is the square root of 5 over 2. So indeed we see the square root of 5 coming up with the length of this, and it's in fact the square root of 5 divided by 2. Now, this is the number we want. This is the number we get, as I indicated earlier, when we divide something in mean and extreme ratio. So now we have to go from the square root of 5 over 2 to the square root of 5 over 2 minus 1/2, which is, of course, something which is hardly worth mentioning in our terms, but as you'll see for Euclid, it causes some trouble. So he says, let EF be made equal to BE. So there's BE, and I just draw, using a compass if you like, I draw FE of the same length. And then I draw this square on FA. So the square FH stands for the square, whole square. I draw that square on AF. And then AH is obviously equal to FA, which is this distance, which was this, by construction, square root of 5 over 2, minus this, which is 1/2 the side. So it's the square root of 5 over 2 minus a half. So there he is. He's faced with the task now of showing what? That FA, which is equal to AH, is that AH is, as it should be, the square root of 5 over 2 minus 1/2. In other words, that indeed H is the point where this line is divided into extreme and mean ratio. So he has to establish this equation with the letter H replacing the letter C. And let's just do it. We have enough time to do it. So, as a first step, I've got. So here's what is asserted, that the rectangle on AB and BH, so on the full line here and on the shorter of the two pieces into which it's been divided, is equal to the square on the longer piece. That's what he's trying to show. And as a first step, we need this relation, that CFFA plus AE squared, so this is the area of a rectangle, and this is the area of a square, is equal to EF squared. That's another square. So let's just, what I claim is that if you think about it algebraically, it means he's working to establish y plus 1 times y plus 1/2 squared is equal to y plus 1/2 squared. Now, if you multiply the right side out, you see that I hope that it's equal to the left side. But let's see, CF, there's CF, there's FA, so CF, FA, and FA is the same as this. So if you like, CF, FA is in effect the area of this rectangle, plus EF squared. Now, EF is the same as EB squared. So it's CF and AE squared, but AE is that. So let's just leave that. We'll prove this algebraic relation later, and let's then just complete what we're trying to do. So EF squared, which is what is on the right there, is EB squared, because we just constructed this line to be, so this to be equal to that one. But here we have, he's going to use, as we did implicitly up there, Pythagorean theorem. This is the one place where we've used it, is equal to this square is equal to the sum of the squares on the other two sides, AE squared and BA squared. So we have this relation, EF squared is this, and we have that, so we have CF times FA, which is what's left over up here when we remove this, is equal to BA squared, which is what's left over here when we remove the same thing. So CF times FA is equal to BA squared. Now that should do it. CF is this. No, it won't quite do it. CF is this, if you like. FA is either this or this. So we have the area of this is equal to BA squared, is equal to this. And what we do then is we subtract this rectangle from each, and we're left in the one case with this, FH, and in the other case with this, which is this. So this rectangle is equal to this square, and I think that's what we wanted, namely, this is the rectangle, one side of which is the short interval, the other side of which is the same, equal to the whole line, is equal to the square on the other one. So that's it. And I guess the lesson to be drawn from this is that in all the construction of the regular pentagon, this is the point and the only point where the Pythagorean theorem is used. So this is the point at which we exploit our ability to construct the square root of 5. Now, proposition 2.6 is a proof of this relation, which is again, that was a special case. So we used it. We used a special case which Euclid expresses geometrically and which that he has to prove geometrically. And I think because my hour is up, I'm not going to prove it. If you think about it, what it says what does it say? Yes. You see, let me just interpret this. Here is x, is AB really. Y is BD. I've taken a straight line, which is the line AB, and I bisected at C, and I add in a straight line BD to it. This I add to it. The rectangle contained by the hole with the added straight line. This is the hole with the added straight line, and the added straight line, which is this. So this is the added straight line, and that's this. So the rectangle contained by the hole with the added straight line and the added straight line is that, together with the square on the half. Well, this is a half. So this is the square on the half is equal to the square on the straight line made up of the half and the added straight line. Well, there's the half, and there's the added straight line, so there's the square made up of the two. And what does it say? It says that this plus this is equal, the area we're speaking of is equal to the large area. Now, I hope that's clear because we just take this little piece here and put it over here. So we have, when we add this and this, the result is what we get by adding this part of it and this part of it and taking this and putting it over here, which comes out to be the square. And the Euclid, as you can see, had to work at it. Well, we don't have time to work at it, and we actually don't have time to do the last proposition, but I feared this, and in any case, I was going to cheat on the last proposition because I think we all, at this point, have an idea, some idea how Euclid does things, and so it seemed to me that it would be appropriate to prove the last proposition by analytic means, which is much faster. Also means that I could put it at the end of this lecture, at the beginning of next one. So I'll put it at the beginning of next one as our introduction to analytic methods. And because I think that these Euclidean proofs, they are fascinating, but you have to think about them for a long time, and I'm not quite sure that you would want to see any more. I could do it if you like, but by popular demand I would do it, but probably useful to do something in an analytic way. And what we'll do next time then is we're really, after giving the first line of Descartes' Discours de la Méthode, which is a lovely first line and which you can look forward to, which will be the only, so to speak, amusing part of the lecture. We will then do analytic geometry for an hour, more or less, and get on there. Not only, so we'll leave the Greeks and we'll not only skip the Renaissance, but we'll get right on into the 17th century. But it will be, I think, just a little dull. But anyhow, and I point out that we're moving. So it'll be in the West Building lecture room. No matter what you see or hear otherwise, it will be in the lecture room and not the seminar room. Okay, well, thank you once again for your attention.